Good. So now I switch to English and we talk about collider physics. The first lecture is on colliders and their operating principles. So we start with an introduction, then discuss the concepts that enable the construction and the operation of the most important contemporary colliders. And we also look a little bit into historical developments because it's just a lot of fun to do. And then we investigate the current energy frontier, which means the highest energy colliders that are in operation today and in the future. And the same for the luminosity. Luminosity means, in principle, how much data you can accumulate per second and over a fixed interval of time. So it is, in principle, a measure of the rate of events or the size of the data set. And finally, we look at an overview of the facilities that are in operation worldwide and the future concepts, in fact, including the European Strategy for Particle Physics, which was updated this year. I put here some links. I will do this for all my slides that I'm showing. I may update them before I upload the slides. These are not complete. These are links for me mostly. You don't have to read through these, but you can find more information on the more difficult subjects that we're going to discuss. So let's start, because we have to discuss experimental particle physics essentially at all energy scales. Why do we have to discuss all energy scales? Because we want, in fact, to investigate the phenomena at the smallest length scales, because we think this is where the fundamental physics resides. Now, if you go to small length scales, you will have small wavelength, but because the energy goes with the inverse of the wavelength, it means that at some point, you will exceed the energy that's required to produce a new particle. You could take a proton and try to look inside the proton, okay? So just take a proton and try to X-ray it. If you shoot a highly energetic particle into it, at a length scale that's much smaller than the proton, it will begin to create new particles. In this sense, it is not possible to passively observe structures below the length scale that's given by the threshold to create new particles. Because if you do this, you don't have a passive observation anymore. If you increase the frequency of, for example, the light particles, the photons, so much that you achieve the smallest length scale, you inadvertently begin to create new particles. In other words, you are led from passive observation to collision. Hence, there is no passive observation below at the lowest energy scales. It's above the highest energy scales. It's always a collision. We think of this usually that we have some point-like particles which exchange force carriers. That's for what is the purpose today. That's the thing. That's the concept. That's the idea of particle interactions that is sufficient. What is a collider? This most simple collider is an old TV set based on a cathode ray tube. I think you're still old enough to remember these TV sets. I certainly am. So here you have a cathode ray and a heater which produces an electron beam. And this electron beam is then focused with magnets, and it's deflected with magnets and with electric fields. And then these electrons hit the screen. And except for the screen, all the other parts we find in a particle accelerator as well. So really these old TV sets, they are just particle accelerators that shoot an image at the viewer. It stopped here at the screen so that you can actually see something. But it's not very far, particle accelerators are not very far from everyday objects if you view it like this. Good. Another thing of introduction, now we have the very general introduction. Now we need to discuss politics and units. Why do I say this together? Units, we have the SI units, kilogram, meter, and seconds, which we use when we relate to everyday objects. This includes the currency, euros or Swiss francs or whatever. This is because whenever we use SI units, then you know that we are talking about something that somebody has to pay for. If we talk about megawatts, terawatts, and stored energies in the collider, then we use SI units because we know what the cost for electricity is, and we have to give these numbers to the funding agencies so that they hopefully pay for it. When we are doing physics, we are having fun, okay? We are not using SI units usually when we use physics. We use natural units. What are the natural units? The natural units are based on the language of particle physics. There are a few constants of nature that we use. One is h bar, the numerical value is given here, and the speed of light, roughly 3 × 10⁸ meter per second. And then there is the unit of energy, which we conventionally choose to be usually nowadays 1 gigaelectron volts, which is numerically just 10⁹ times the electric charge of the unique electric charge, because 1 electron volt is the energy that an object with a charge of 1 electron accumulates if it traverses a potential of 1 volt. Okay, that's 1 electron volt. It is just a unit for the energy. Now we use GeV, and GeV is you can see it here. It's a certain number of joules, so it is an SI unit. So the unit of energy is GeV. The unit of the momentum is mass times velocity, is GeV over c. The unit of mass, because you know E equals mc², so the unit of mass is just the unit of energy divided by c². And similarly, you can use the Planck's Wirkungsquantum, which is energy times time, to define the unit for time, which is h bar over GeV, similar for length and for area. So this top block of units here, these are just factors of SI units. So these are the SI units. In fact, we can express the time in these rather crazy numbers, and you can calculate that the lecture today, the first part, which is 90 minutes, lasts 8.2 × 10⁻27 h bar over GeV, in case you find this helpful. Now, that was the SI units. In natural units, we simplify this because we don't want to carry around the C's and the h bars. We put them to 1. H bar equals C equal 1. That means if you have had fun and you have calculated something in your theory lecture, you will get an answer mostly in units of GeV. Energy, momentum, and mass all have the same dimension because we put C to 1. Or inverse GeV, if you calculated the time and length, or inverse GeV² for an area. If you want to change from natural units to SI units, you have to put the units back. And if you put the unit back, you have to know what you calculated. So you have to add extra information. Now let me try my iPad here to show you how this goes. So if you calculated a momentum of 10 GeV, and you need to know that this was a momentum and not a mass and not an energy, then you have to change this number to 10 GeV over c, the speed of light, according to the table here, and then insert the numbers, and then you will get the correct answer. Okay, and this works for all quantities, of course. And to make this more easy, I put here certain numbers from the cookbook. H bar C is 200 MeV times Fermi. A Fermi is a femtometer. 10 to the minus 15 is the diameter, very roughly, of the proton. And that's 200 MeV, that's the pion mass. The proton mass is 1 GeV. So this is like, H bar C is like 20% of the proton mass multiplied with its diameter. And similarly for the areas, I should introduce it now maybe, the unit of barn. The unit of barn is a unit of interaction cross-section, so it is an area. A barn is 100 squared Fermi. If we think of a proton, I just said that a proton, let me change the color, yeah. A proton has a diameter of 1 Fermi, and here we have 100 square Fermi. So let's just make a drawing and of 100 little squares. This should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this should be little squares. Then you put a proton in the middle. That's the size of a proton, and 1 barn is 100 times this 100 times the area of a proton if you look at it from one direction. Okay, so 1 barn is a gigantic cross section. We collide protons. Their cross section, their cross section, if they were hard scatter objects, would be much smaller. It would be 0.01 bar. So this is just to explain you what a barn is, how big the area is that we label with a barn. It comes later when we discuss cross-section values. Now let's look at enabling concepts. Begin to look at the enabling concepts a little bit historically. What were the first particle colliders? For particle collisions, you need high momenta of the colliding objects, and that works best with charged particles. And for this, one can use an electrostatic generator, the Van der Graaf generator, which is depicted here. It has a rubber band here. So there's a rotating rubber band that accumulates, there are metal brushes here and here. It accumulates electric charge at this top dome. And that works up to 2 MeV, nowadays up to 5 MeV. These Van der Graaf generators are partially still in operation for low energy experiments and for outreach activities. In principle, this is a great idea, but you cannot do it indefinitely because at very high voltages, you maybe know from electrostatic that you get corona discharges if you have sharp edges, and at some point even softer edges will have corona discharges. So above the megavolt regime, this really becomes dangerous and difficult to handle. Also, you have leakage currents. Nevertheless, these Van der Graaf generators can be used to accelerate charged particles. It's a better idea, in fact, to use an AC current, a Wechselstrom. And and use the Cockcroft-Walton generator, which was invented by these two British physicists in the 30s. So they used this ingenious set of diodes and condensators to multiply the voltage of a driving force of a driving generator. If this generator has an oscillating potential difference here that is pushed up these diodes, and the voltages are multiplied. This is then connected to a linear electrostatic accelerator that's depicted here. So you have a very high potential difference from the top to the bottom, and you would shoot charged particles from the top here onto a target at the bottom. This is important because in some sense here is where particle physics starts. One can put the beginning of particle physics at various points in time, but this is the first disintegration of an atomic nucleus. It was in 32, and protons were shot at a lithium target by Cockcroft and Walton, who invented this. And lithium proton, we now know they didn't, but they assumed that the mass 8 nucleus formed that immediately decays into 2 helium atoms and release, well, now we know it releases also 17 MeV. They found the helium nuclei in a zinc sulfide, on a zinc sulfide screen, because the helium nuclei are just alpha particles. And alpha particles could be detected because in the 30s, I mean, the golden time of the studies of radioactivity were the 10s and 20s of the 20th century. Hence, studies of alpha particles were already well developed. One had zinc sulfide screens, and well, Cockcroft and Walton shot protons at lithium and discovered them. They interpreted this correctly as a disintegration of the nucleus. It was the first time that we could do such a thing. So that's electrostatic force. Oh, here is an still operated, I think, Cockcroft-Walton generator. You know this maybe from the ancient science fiction movies. Those apparatus inspired the imagination of the movie directors, of course. Good. So now let's move towards the real deal. Enabling concepts of accelerators that are still in operation. First is linear accelerators, because linear accelerators are always used. Even a circular accelerator has to have a linear pre-acceleration stage. It's always difficult. It is very difficult to accelerate protons and keep track, or electrons, and keep track of the varying speed that those particles have. In principle, in the beginning, you want a low frequency because these particles move slowly, and at the end, you want a higher frequency, and you also want high power. Now, technologically, high frequency and high power together is very difficult. Once you have high frequency and you have high power, it's very difficult to change the frequency. There is very little technological means to do that. So the ingenious idea of the two physicists, Wideröe and Alvarez, is the following. Look at these drift tubes here in the bottom. You have an electron or an ion source, it doesn't matter, just particles with charge, and they at very low speed are injected into drift tubes, and then these are accelerated. And the length of these drift tubes is adjusted to the speed at which these particles move. And because it is adjusted, one can use the same frequency at all acceleration stages. And the length here take into account the acceleration, but it also takes into account the relativistic correction, because you know that once the electrons are relativistic, or protons are at the relativistic speeds, their speed in the lab frame as a function of energy does no longer increase so much, because the speed of light is the highest attainable speed in all reference frames. So the ingenious idea, I hope you can understand this, is to reflect the dynamics of the acceleration in the length of these drift tubes, so that we can operate it with a single high frequency, high power voltage source. There's a picture from the CERN microcosm where I think it's from the Lab Collider, I'm not sure, where such a structure is shown. Now, that's a linear accelerator. In principle, it's great. You can build it arbitrarily long, in principle, if you have enough money. The problem is that the particles don't come back. So once you've built it, you can achieve a certain energy, and to increase that energy, you have to build it longer. If we put the particles on a circular orbit, then in principle, they come back and we can increase their energy more. And hence, usually, depending on other limiting factors, we can achieve higher energies. So this was the idea of Vidaurre and Alvarez. Both of them, in fact, were PhD and short in the first, so shortly after PhDs after their PhDs in the 30s. Vidaurre did this work and other work for the Germans, by the way, because his brother was in the resistance and he got caught, and he had hoped to improve the situation for his brother. I just read this before the lecture. So there's always real people behind these inventions. So that's the linear accelerators. Now let's look at the circular accelerators. This, of course, is a very difficult task, because you can imagine for a linear accelerator, if the incoming particles, they are a little bit deflected, it doesn't matter that much. However, if you put them into if the particles are in an orbit, the beams have to be highly synchronous. Otherwise, if there's a small energy spread, you would very easily lose these particles after many turns. The first idea that I want to discuss, because it's a really great idea, and I want to show you how ingenious the early particle accelerator physicists were, is the betatron. The betatron, beta comes from beta rays, so it's electrons from highly energetic electrons from beta decay of radioactive materials. Look at the sketch to the right. This is a magnet coil. There's a symmetry axis that's vertical. It has a donut-shaped vacuum. The electrons are injected into the donut-shaped vacuum here in a plane that's, I try to show this with my video, in a plane that's perpendicular to your screen. So here they are injected, and the magnetic coil is the secondary coil of a transformer that's operating at several hundred hertz. Now, let me draw that. So here we have time, and here we have the current. For example, the current in the magnetic coil, and this is oscillating sinusoidally, and here happens the injection, And at this point happens the extraction. So we talk about this quarter wave here. I need to erase it again. What happens now? You inject when the B field is low, and the B field rises. Because the B field rises from Maxwell equation, you get a curl on the electric field. A curl on the electric field means that the electron has an electric field that's in the azimuthal plane and accelerates that electron all the time. So one exploits the varying B field to have the electron accelerating on the circular, like this, on the circular orbit it takes in the betatron. At the same time, because the B field increases, it makes a stronger Lorentz force, and because the energy by the curl of the E field of the electron increases, the magnetic field also increases and keeps the particle in stable orbits. There are several thousand turns possible until the driving current reaches its maximum, at which point the beam would be lost, but at that point it's ejected. So the idea to exploit the curl of the E field and at the same time have the increasing magnetic field compensating for the rise of the energy of the particle that's being accelerated is an ingenious concept that's realized in the betatron. By the way, Wideröe from the previous slide, he also worked on the betatron and for the Germans. And the German 6 mega electron volt betatron is here shown at the bottom right. Nowadays, we have better control on high frequency, high power voltage and current sources. And hence, nowadays, we do not need to rely on this betatron idea. But nevertheless, historically, it was the first time that we could accelerate particles that were moving on a circular orbit. Good. That was the betatron. Let's move to the cyclotron. I will stop after the cyclotron and let you ask questions. The cyclotron is also for acceleration of particles moving on a circular orbit. We have in the middle here, we look at the cyclotron from the top, okay? Here in the middle, there is a source of particles, and the particles are ejected at very low energy. Then there are these D segments. It's actually just the capital letter D, because these look like Ds. So here we have two segments, and they are on an oscillating electric field with opposite phases. So what happens to a particle that moves at such a trajectory? We can do the calculation that's written here to the left. I will do it again because I like my new iPad. I will do it again, just the same calculation to the right. We have the centrifugal force is mv squared over r. We do a non-relativistic calculation. So that's the centrifugal force that the particle feels that's on this circular, actually helicidal, but let's say circular trajectories. And this equals the Lorentz force. So the Lorentz force is just Q times Vx_b. The magnetic field that's used here is a constant, and it is perpendicular to the plane. So the X product is just Q times V times B, where I'm using the magnitude of all these vectors. And from this we can cancel 1v, and then we can compute v over r, velocity divided by radius, that is the frequency, the cyclotron frequency, an angular frequency because there's a 2 pi, is just q times b divided by the mass. And this is important because it means that the cyclotron frequency is independent of the velocity or the radius. So what happens is that you eject the particle, it goes on a low, because it has little energy, it goes on a small radius. The radius increases because the electric potential forces it to, the particle is pushed to the other side and then it is pushed back, and the radius increases, but because of this formula, the frequency stays the same. In other words, again, you can use a single frequency acceleration, and that's much more easy to handle, okay? Now, there are, of course, relativistic corrections. So if the electrons or the protons or the ions, doesn't matter, are pushed back and forth on the helicital path, keeping the angular frequency of this movement constant, that only works until the speed becomes relativistic. And you know that it's a simple way of having relativistic correction is making the mass of the particle dependent on the velocity with the Lorentz gamma factor. So the gamma factor for at rest is 1, and when you approach the speed of light, it becomes infinite or very large. So it tells you that the frequency becomes lower when lower than it would be in the non-relativistic calculation. Now, why am I telling you this? I'm telling you this because the world's largest cyclotron is the Triumph cyclotron, which accelerates protons up to 520 eV, where the speed of where beta, so the velocity divided by the speed of light, is 75%. So these are already relativistic. What people do here is they compensate for this relativistic correction by slicing the detector open. That's why it has this, this star-shaped pattern. So what happens here is that the protons are injected here and then they circle outwards, and the geometry is such that these segments provide the B field, the magnetic field, over a wider area of this movement, the more outwards you come. So hence, in case you did not believe in special relativity, I'm sure you do, but in case there are still, well, in fact, every few months or so, somebody tries to explain to me why Einstein is wrong. But here, this the Triumph cyclotron implements the Lorentz gamma correction into really the geometry of the detector. I think it's a beautiful application. I also think it's pretty complicated to understand this if you hear it for the first time. So I stop now, and since nobody said a word, I understand. Does anybody have questions? Yeah, a little bit shy. I can ask the people I know better. Lucas, do you have a, did you follow?
Sure, yeah.
Okay, very well. So I will upload the lecture to YouTube. You can hear what I said, you can rehear it if you want. You can also use the forum on the Moodle to ask specific questions. And you can also send me questions and we can discuss them next time and tell me, like, I did not understand how cyclotrons function and so on, and why is this and that important, okay? So we've discussed now the BETATRON and the cyclotron, both of which are ingenious ideas that exploit basic physics concepts, special relativity, and so on, to reflect the limitations of the time. And the limitation of the time was that it was not easy. It's still not today, but it's not possible easily to control the power of an electric of a voltage or a current and the frequency at the same time. Good. Let's move to a realistic picture. Synchrotrons. Synchrotrons are circular accelerators that run synchronously. That means typically that means the beams are bunched and return to the same place in a highly controlled fashion. So we have here again what I showed already in the introduction, a picture of a depiction of the LHC collider. What does it consist of? So here you have the circulating beam. It's 27. The circulating beam pipes. It's 27 kilometers in circumference, and we need dipole magnets to bend the trajectories of the charged particles. So it's a circular collider. Particles come back, but you have to make them come back. Therefore, you need dipole magnets to bend the trajectory. If you want to bring them to collision, one also needs a quadrupole and sextupole magnets to do so, because otherwise the beam is not focused. So that's the way that's how charged particles are bent on their circular path. We also need to accelerate them, and the electrons and protons are accelerated by so-called radio frequency cavities, which are cavities that guide an electric wave just behind the bunched beam. So a bunch of particles comes along and an electric field is guided behind it so that all the particles get pushed. And we don't have to have an enormous push, because the particles are going to come back and we can push a second time. It's difficult to have because you need to do this with very high frequency. We talk about 400 megahertz, and we need megawatts. So we need special power sources that can achieve this, and these are klystrons. We'll discuss what these are in a little bit. But okay, radio frequency cavities for acceleration, dipole magnets to bend the beams, and then quadrupole magnets to focus the beam and to make the collision. That's the basics. That's the things that you need. The rest is the pre-acceleration complex and an injection system, which takes a lot of the money, but it's, in a sense, it is more of the same concepts used in different ways. And once you have the beam, when you've done your collisions, you need to get rid of the beam. The beam stores enormous amounts of energies. If those are released in the detector is destroyed. So one needs a beam dump and extraction system. In fact, the beam dump system at the LHC would be here, very close, worryingly close to the CMS detector. If something happens in the beam dump system, then indeed it would mostly damage, it would damage the CMS tracker at the very least. Good. What are the, once you've built such a thing, this a synchrotron with your dipole magnets, with radio frequency cavities that accelerate the protons, you could think that the limit is the sky and you could just accelerate all the way. However, that's not the case because there are limitations on the energy that's achievable. There are two different limitations for the different types of colliders. For E+ and E- colliders, the limitation is synchrotron radiation. An accelerated charge radiates electromagnetic energy. For electrons, in circular colliders, this is the limiting factor. We'll do an extensive calculation of synchrotron radiation today because it's a fun calculation and it's very important. It sets the boundary for the discussion of the strategy of particle physics in the 21st century. So these are really the rock solid foundations of particle physics since 100 years from the technological perspective. Proton colliders like the LHC hardly have any synchrotron radiation. It's completely negligible, and we'll see why. So if there's no synchrotron radiation, what's really limiting is the magnetic field you can put into your dipoles. These are superconducting dipole magnets. Unfortunately, one cannot raise the magnetic field in a superconductor indefinitely. There's a hard limit to that. And it's 8.3 Tesla for the LHC magnets, and that leads to an energy limit of 14 tera electron volts. We're going to calculate that in a little bit. But let me just say, so this is the LHC overview with the 4 detectors, ATLAS, CMS, ELIS, and LHCb. We're going to learn about the detectors in other lectures, not today. But here they are. And similarly, the Super KKB E+ E- collider, it is not on the energy frontier. It does not have the highest achievable energies. It does, in fact, have the highest rate of data taking. We say that it is at the luminosity frontier. So there are the most collisions, E+, E- happening per unit time at this collider. It is in Japan. So these two are, in a sense, the two more, I mean, there are more accelerators. We're going to look at the list, but these are the two main currently operating accelerators, one for proton, that's the LHC, and the E+, that's Super KKB, that currently deliver new results, more or less on a daily basis. Good. So let's look a little bit closer at these. The LHC accelerator complex. This is also not to scale, okay? It is 100 to 150 meters below the surface. So that's the LHC accelerator. Here is Geneva, and these are the Jura Mountains. This is the Lake Geneva, so it's at the Swiss-French border. In fact, the beam crosses the border twice, so it's in two countries. Well, that's where it's located, 27 kilometers in circumference. The main experiments are CMS, it's here. Here are the main, here are our main, the main labs and the hotel and the cafeteria, at least most of that's here. This is where ATLAS is. CMS is 30 minutes drive away, 20 minutes drive away if you're there. And then there are the other experiments, LHCb and ELIS. This figure includes the pre-acceleration stage. Here I'm not going to go into details. There are several hundreds of experiments being conducted at CERN in the LHC, in the vicinity and the wider area of the LHC accelerator complex. Particles start here. That's the linear accelerator, LINAC. this is where the acceleration starts, and then protons go into the booster. From the booster in the proton synchrotron, from the proton synchrotron in the superproton synchrotron. The superproton synchrotron is the predecessor. Here, protons are accelerated to an energy of 450 gigaelectron volts, GeV. And from here, they are injected into the LHC tunnel. And once the beams are filled with protons at the injection energy, the beam is ramped using the radio frequency cavities, and the dipole magnets are ramped up at the current in the dipole magnets is ramped up at the same time, so that the energy is then increased to 13 tera electron volts. At the collision vertex, each beam currently has 6,500 GeV. Because the proton has a mass of very roughly 1 GeV, it means that a proton has a relativistic gamma factor of 6,500. So a proton disk, because it's also Lorentz contracted, and the second proton disk move through each other, and that's what we call a proton-proton collision. But we're going to talk about the collisions more. I just want to mention it now. Because, what's the time? Now we hit the energy frontier. And we have to do our first calculation. Let me briefly walk you through the calculation, and then I will do it. We are now going to calculate the power dissipation of an accelerated charge. That means we put a charge in the vacuum, a single charge of a single particle with charge Q. We can calculate, we know the potential, it's 1 over 4 pi epsilon 0 times Q over R. You can already see I include the epsilon 0. I also include factor of C. I'm going to use SI units. It is because somebody has to pay for the power that we are dissipating here. So we're going to use SI units. Good. The electric field is the negative gradient of the potential. So it's just Q over 4 pi epsilon 0 times 1 over R squared, and it points into the radial direction. So now we do our calculation. I will do it by hand, but first I would like you to look into this picture here. What we have here is a radial electric field of the electron at rest. And now we imagine that for a short period, delta t, an acceleration happens to a non-relativistic speed of delta v. So we are saying that we have a particle at rest and we give it a little kick. And after that little kick, it moves at a low velocity. This is not now. It's not a relativistic calculation. This means it will after the acceleration, it will still have a radial field. However, that radial field is moving, and so we get a shell where there's a displacement in the electric field that's moving outwards with the speed of light. Now, this shell of displacement carries away energy, and the amount of energy it carries away is the synchrotron radiation. It is the power dissipation that comes from the acceleration. We're going to calculate it now, and I walk you through the steps. I know this is difficult to follow because I cannot look you in the eye and see your facial expression, and in fact I need it. I need it because I usually need to know when to go slower and when to go faster. I have uploaded a YouTube video of this calculation that is very detailed and very slow. It lasts 32 minutes, and it's just the calculation that we are doing now. please, I'm going to calculate it now. Interrupt me in case you don't understand a step, even though you may feel reluctant. It's really, I mean, it's a lecture. It's unfortunate that I cannot see you, but do it. If you don't understand something, you can also ask me next time, okay? I'm somehow trying to make up for our lack of social interaction that we would usually have in the lecture room. So stop the whining. Let's do the calculation. The first we have to realize, and that's actually the only thing that's not straightforward, and that's a bit that needs a little bit of thought, is there is a perpendicular component in the E field, is exactly where these two arrows point, and there's a parallel component. Parallel means with parallel to the R vector, and perpendicular means perpendicular to this R vector. So perpendicular means actually azimuthal here. You can convince yourself, I hope, just by looking at the picture, that this distance here is delta V, the velocity that we have, times t, so it's proportional to the time that has passed, times the sine of theta. So this is 0 in the direction of acceleration, and it's maximal normal to it. The orthogonal displacement, the little piece here where I move my mouse cursor, is just c times delta t, because this wave moves outwards with the speed of light, and delta t is the time we used up for the acceleration. So let me give you the calculation now. After this calculation, we make a break. Yep. I'm trying to share. I will stop this share now. I hope you have the slides open in the browser. Otherwise, it will anyway be self-contained. Maybe you don't need them. I will now share my screen here. I'm sharing my screen here. I go to this blank page here. Okay, and I start my calculation. So we had this radial picture. It had a little bit of a displacement here, and we had in this direction, we had delta V times t times sine theta. I think it doesn't hurt if I go a little bit slow now. Let me erase this. So that's this displacement. And this displacement here is just c times delta t. Okay. C times delta t. So the important thing is that we can now take the ratio of the two, and the ratio of the two is delta V times t times sine theta divided by c times delta t. If you've come that far, you're done. The rest is really applying a few tricks and putting everything together. Now, we know that phi of r, I have it on the slide, I'm writing it here again just for the sake of completeness, is 1 over 4 pi epsilon 0 times q over r. I do remember from when I gave the lecture the first time that this was the hardest part in the whole lecture, and it comes at the very beginning, so it is discouraging, but it's not going to get any worse. So we take the electric field as the negative gradient of the potential, and it is q over 4 pi epsilon 0 times r over r squared. Okay, as promised, the rest is straightforward because we can now compute, we can take E parallel from here, and we can compute from this equation the perpendicular component, and it is only q over 4 pi epsilon 0 divided by r squared. Oh, that was wrong. There's a cubed here. Divided by r squared, and we get the acceleration here. It's delta v divided by delta t, because acceleration is really what drives the energy dissipation. And the geometric factor is r sine theta divided by c squared. You can already see from the power in r that this is the component that will radiate, that will really radiate the energy. All the higher modes are fall quicker as a function of r. So we write this as q times the acceleration v dot times sine theta divided by 4 pi epsilon 0 r c squared. As I said, we keep all the factors of c. H bar doesn't appear, but all the factors of c, because we're using SE units, because somebody has to pay for this. Now, we know that for radiation that is in the vacuum, the magnitude of the B field in SE units is 1 over c times the magnitude of the E field. You can see this by injecting, by looking at the plane wave solution, for example, of Maxwell's equation. So we know the length of the B field in terms of the length of the size of the B field in terms of the size of the E field for this radiation. That means we can compute the Poynting vector. What is the Poynting vector? The Poynting vector is the vector that describes the energy flow of electromagnetic radiation. In SE units again, it is defined as 1 over mu 0, which is, I think, I forgot. It's, I think, 4 pi times 10 to the minus 7. I'll write it down later. It's a long time. I looked at mu 0. So the Poynting vector is just E xb times times 1 over mu 0. So because we know that the electric field is perpendicular to R, and because it's vacuum, the B field is also perpendicular to E, we know that the Poynting vector must be radial. So we know already the direction. And anyway, we only care for the radial energy flow. And the rest is the magnitude of the E and the B field multiplied with 1 over mu 0. So we can just, because the magnitude of B field is the magnitude of E field, we just need to square. So let's square. We get the perpendicular component squared, and I square everything that I have here. So it's q squared v dot squared sine squared theta divided by 16 pi squared epsilon 0 squared. Now I write my mu 0 that I get from the definition of the Poynting vector, and then I get a c to the 4th, and then I have, from the B field is 1 over c times c, I get another power of c, and then I get an r squared, which I forgot. And next I use the famous relation due to Maxwell, in fact, that epsilon 0 times mu 0 times c squared is 1. Because Maxwell was successful in calculating the speed of light from measurements of electrostatics and magnetostatics, who respectively are depend on so where epsilon 0 and mu 0 enters. So that's a basic relation in Maxwell theory, which means we can remove one of the epsilons, one of the mu's, and 2 of the c's, because that product is just 1. And now we are ready to compute the dissipated power. The dissipated power is just the space integral over a sphere around this charge times s in the radial component. So we take the Poynting vector, that's this, take its radial projection and integrate over a sphere. And this will be the dissipated power. Let's do it. I take all the prefactors I've just written. It's q squared v dot squared divided by 16 pi squared. I get an epsilon 0. I get the c cubed. Just explained before why there are 3 powers of the speed of light. And I get an r squared. And next we write the volume, the surface integral. It's 0 to 2 pi r d phi times 0 to pi r sine theta d theta. And then I get a sine squared theta. That's the theta dependent term from here. And we can remove the powers of r, which just means that nothing depends on the radius because the energy got to go somewhere. This also confirms that we really are looking at the right term and we can forget about all the subleading terms. And we can now compute. We can now compute this integral. This one we can write as integral of minus 1 to 1 of d of cosine theta times 1 minus cosine theta squared. And this integral is, if you compute it, this integral is 4 over 3. And this integral, because nothing depends on phi, is just 2 pi. So we almost have it. We need to multiply the numbers. It is q squared dot v dot squared divided by 6 pi c cubed epsilon 0. And that's the dissipated power of an electric charge that's accelerated. So we have here our charge with charge q that is accelerated so that it moves with a velocity of delta v. So it was accelerated during a time delta t. And this is Lamar's equation. It gives us superpowers. It's great. We can now take any charged object, particle, take a path, compute the acceleration, and compute the power that's dissipated. I find this great. The problem is now, this formula is non-relativistic. It does not hold for large velocities. But there is a trick now. The trick is called you could call it covariantization. Now, what is this? It's a very difficult term, but the thing is very simple. This here is power. How does energy transform? Energy transforms, if you do a Lorentz transformation, it transforms with a gamma factor. How does time transform? Time transforms also with a gamma factor. These two things together mean that the power does not transform. It transforms as a scalar. So we know for a fact that the quantity here on the left is Lorentz invariant. If the quantity on the left is Lorentz invariant, the quantity on the right is also Lorentz invariant. We just don't see it. And we don't see it because we use V dot. V dot is something that's not manifestly Lorentz invariant. But we can make it Lorentz invariant just by using the covariant terms of the covariant form of the acceleration. And that's the whole trick. So we don't use the acceleration, we should use the momentum. Let's write it in terms of momentum. So if you write it in terms of momentum, this is q squared. We keep all the factors, 6 pi epsilon 0. I divide by the mass of the particle squared. I keep the c. And then this becomes the momentum differentiated with respect to the time squared. And now this becomes, in the Lorentz invariant form, I first write it down and then I explain it. So this becomes minus q squared c divided by 6 pi epsilon 0 mc squared times, and now we write this in Lorentz covariant form. These are now 4 vectors, dp mu with respect to d tau times dp mu with respect to d tau. If you insert this back, this is dp, this is dp, this is minus dp with respect to d tau squared minus 1 over c squared d e over d tau squared. So what have we done here? We've written this in-product of the differentiated momentum in Lorentz covariant form. These are the spatial components. It only here's the spatial components. Because this in-product here of the Lorentz index gives us a minus sign, we add a minus sign in front, and then this cancels with the minus sign from the spatial components that we have here, okay? And this is a relative spatial components. I hope you can read my handwriting. And this term with the energy is the relativistic correction that we had neglected in our non-relativistic derivation. One should say that what I've used here for the momentum, P mu is E over C, and then here we have the spatial components. Okay? If you look at this formula, so this is now the power, this is the relativistic form of Lamar's equation. As it is in the slides. If you insert this momentum, you can check that in the non-relativistic limit, the power is recovered as we've calculated it. And because you know that the power does not transform under Lorentz transformation, which I've shown to you before, we know that this is the correct form. I'm not going to ask you this for the exam, okay? But it needs to be derived because it is important for the following. We've now computed the Lorentz invariant form of the power that's dissipated by an electric charge, okay? So let's do an example, okay? The example is linear acceleration. What happens if we take our electron and put it in an Alvarez-Videroe structure and accelerate it linearly? One needs to do a trick. The trick is, it's always in special relativity, you always have to know exactly what steps you take in your calculation, and then they are simple. If you don't know, then the calculation are complicated. We write the energy momentum relation. With enough time. Plus p squared c squared. And we differentiate it with respect to the proper time. The proper time, tau is the proper time. It's the time that the clock shows that travels with the particle. The differentially related to the time in the lab frame by a factor gamma. Single particle special relativity. So we differentiate, we find E with respect to d tau equals, well, the mass term, that's the rest mass, it's constant. So we find c squared, we find a factor 2 here. 2 times c squared times p in dp with respect to d tau. Fine. Now, write our four momentum. We can write it in several ways. We can write this as gamma m for the component with the energy, gamma mv for the velocity. We can also write this as E, or the 3 component of the momentum. We can also write this, I'm just giving you options that you can check these calculations if you want in all their glory. And here we have beta and c. And we know from special relativity, gamma equal 1 minus divided by square root of 1 minus beta squared. So these are the formulas to the right, I assume that you have seen. The formulas to the left, I'm deriving now. So we can calculate. Let's express the E with respect to the tau. Because this is the new term in the relativistic correction that appeared here. The E with respect to the tau is c squared times p over E in product with dp with respect to the tau. And now we insert, and this is just c squared. Now I use the formulas to the right, times gamma times m times v, divided by the energy, that was gamma times m. I'm sorry, so here's a c squared. Times c squared times dp with respect to d tau. So everything cancels. Except the velocity. So this is just v times dp with respect to d tau. And that's interesting because we can now insert this into the second term here and combine it with the first term for the special case of linear acceleration. So let's do it. The dissipated charge for linear acceleration is our prefactor q squared c divided by 6 pi epsilon 0 times mc squared squared times the dp with respect to d tau squared minus 1 over c squared times the v squared. I now square our result. And the same term appears. It's dp with respect to d tau squared. So this whole thing is just 1 minus beta squared times dp with respect to d tau. So that is just, that term here is just 1 over gamma squared. So that whole thing together is just dp with respect to d gamma times tau, which is dp with respect to dt, which is the time in the lab frame. So we have the momentum change in the lab frame. The momentum change in the lab frame, wait, I'm sorry. This is all squared here, of course. So the momentum change in the lab frame squared, we can for an ultra-relativistic particle. So let's say ultra-relativistic particle means just saying that forget about the mass. That's an ultra-relativistic particle. We can replace this with the E over dx. The E over dx is the energy change of the particle. And what are typical values? 25 mega electron volts per meter. Look, if you have more than 25 million volts on a meter, it's likely that the thing explodes, or that there's a gigantic spark that melts everything. 25 MeV per meter with classical appliances, so that's not collisions with other particles or something like this, so just electric fields, is a good number of what can be accomplished technologically. So we have an energy change per meter of 25 mega electron volts. It's hard, it's a good, I mean, we can achieve a little bit more. We can achieve, one can achieve much less. It's a good number of what can be achieved. So this energy change is for an ultra-relativistic particle, the change in momentum per time is given by the energy gradient on a distance, on a certain distance. So we have 25 mega electron volts per meter. And we can insert this now, everything together, in our linear acceleration Lamor formula, which is q squared times c divided by 6 pi epsilon 0 mc squared squared times dE over dx squared. And now we run some numbers, okay? So that's epsilon, wait, this is unreadable, I'm sorry. Now we run some numbers, practicalities. This is 25 MeV per meter. The mass is 0.911, it's the electron mass. 0.911 times 10 to the minus 30 kilogram. I did write down what epsilon 0 is. Epsilon 0 is 8 point, in SI units, 854 times 10 to the minus 12 coulomb per voltmeter. That's epsilon 0. And c, the speed of light, is very roughly 3 times 10 to the 8 meter per second. And now you use your pocket calculator, inject the numbers, and compute. This is 1.1 times 10 to the minus 16 watt, which is tiny. It's a vanishingly small power that's dissipated by linear acceleration. You can also compute the energy efficiency, which is just which is called eta. It's on the slides. I don't go into detail. It's the energy efficiency. The energy efficiency of synchrotron radiation by a linear linear acceleration. So we take the p and divide this by 1 second, and divide this by the E with respect to dt, and it is also tiny. It comes out roughly 10 to the minus 13. 10 to the minus 13 means only a fraction of 10 to the minus 13 of the input energy is converted into synchrotron radiation. That's nothing, absolutely nothing. It's vanishing. This means we've calculated, I've spent a lot of time calculating something that is zero. It is to show you that linear acceleration really is completely, synchrotron radiation can be completely neglected. Now let's do something else, and that's a lot faster. Let's do circular motion. The calculation is a lot faster. Don't worry, we are almost done. And it's a completely different game. Let's look at the p with respect to dt. It's the thing that we need. It's the thing that we need for our relativistic calculation. For a circular motion, this is just the frequency of the circulation times p. You only need to insert, for example, to insert sine. For a circular motion, you will have, for example, px be proportional to sine omega t, and then you get this factor omega in front. Omega is the velocity of the particle divided by the radius of your accelerator times the momentum. So, because the velocity for an ultra-relativistic particle is very rough, I mean, it's almost the speed of light, we can write c over r times p, and c times p for an ultra-relativistic particle, I write it here, is E over R. So with this equation, we go again in our Lama formula, the relativistic one. We write, so that's one thing. I'm sorry, the second one, E with respect to dt is 0. Circular motion does not change the energy. We only have, we consider a particle that moves in a circular orbit at the same energy, okay? It is an acceleration because the path is spent, but the energy does not change. So with these two results, this one and this one, we go into Lama's formula, and it is q squared times c divided by 6 pi epsilon 0. And now I have the p with respect to dt squared, and I put my gamma squared in front here. The gamma squared comes from the differential here. And we can continue writing this as now we're almost done, q squared c divided by 6 pi epsilon 0. I write the gamma factor as the energy of the particle divided by mc squared, and squared because it was a gamma squared, divided by mc squared, and now I inject my expression for dp with respect to dt, and it is E over R squared. I know that these steps go fast, okay? But you have a recording already, in case you want to go into more details or do it yourself. Q squared C times 6 pi epsilon 0, 1 over mc squared to the 4th power times energy to the 4th power divided by radius squared. So this is proportional to e to the 4th divided by m to the 4th divided by radius squared. So here we have the basic property of the conception of particle colliders that we discuss since 80 years probably, okay? This is absolutely basic because what can you see with these enormous powers of 4 here is the following. First of all, if you compare electrons to protons, the mass of the proton divided by the mass of the electron is very roughly 1,800. And if it gets a 4th power, we talk about factors of 10 to the 14. In other words, because it appears in the denominator here, synchrotron radiation for proton is negligible. So we already calculated that linear acceleration has no synchrotron radiation. Now I'm telling you that protons on a circular orbit also don't have synchrotron radiation. It's also vanishing because there's a 10 to the 14 involved. However, electrons on a circular orbit have a very large synchrotron radiation. We're going to look at numbers soon. The calculation is over now, we're done. And you see, what I want you to read off simply from this expression here, what I want you to read off is that electrons at the circular collider are limited by synchrotron radiation, and it's very hard to beat. The mass of the electron is small, you can do nothing about it, okay? You want to increase the energy, your synchrotron radiation increases with the 4th power. That means it increases, it's a small number at first and you don't see it because the 4th power of a small number is a vanishing number, and suddenly it explodes and it goes through the roof. You want to double your energy, you have 16 times the loss. This is unacceptable. In other words, electron colliders can go to a certain maximum and then they cannot go further. The only thing you can do to reduce this is to increase the radius of your accelerator, but that's extremely expensive. That's the tunnel. So instead, and the tunnel only enters with squared its radius. The energy that you want, it enters with the 4th power. And so you're dead. You want to go from 100 to 200 GeV, for example. You have 16 times the losses. To bring it down, you need a radius that's 4 times as large as you had before. The radius is 4 times as large. So it's impossible in principle. That's why electron circular colliders are limited. I stop, I go back to the slides now. I need to share them again. 1 sec. And the last thing we do is we look at the numbers. So protons, I'm sharing. Protons at the LHC have an energy loss per turn of 7 kiloelectron volts. That's nothing because they travel with TeV and they lose only KeV. That's a factor of a million, right? So only a millionth they lose. So you can have these protons circulating for 1.5 days and they use only a fraction of the energy. However, for electrons at the lab collider, so it's the same tunnel, 27 kilometers, we have 70 GeV and we lose only 70 GeV. That's 100th less than the 70 eV. And we use 100th more. That's 4 orders of magnitude per turn, which means that an electron beam has a lifetime when it's synchrotron radiation limited, it is a lifetime of milliseconds. And if we go from 70 GeV electron energy to 100 GeV electron energy, the loss per turn go from 700 kiloelectron volts to 3 gigaelectron volts. This is a 50% increase in energy, and we get a factor of 4 in energy loss. So 50% versus a factor, 50% energy gain and a factor 4 of loss. This is why synchrotron radiation is so important. It really decides what collider we can build. It's important for it's important for electrons in a circular collider. It's not at all important for protons in a circular collider. And it's also not important for linear accelerators. Good. So the last thing, I'm not discussing this in great detail. I find it's interesting. The synchrotron radiation, we computed it. It has this sine squared. It has this sine squared theta dependence. And the sine squared theta is orthogonal to the direction of acceleration. So if we have a particle on a circular orbit, this donut shape is the acceleration points inwards. So the donut shape is parallel, if you wish, to the circular trajectory. And because of the Lorentz transformation, it is collimated into the direction of the movement. I gave the formula here. It's not important to derive it. Maybe I just put it here for my own education. So the synchrotron radiation from an accelerator is really going into the direction of the movement and leaves the particle tangentially and it just leaves the particle beam and then hits the wall somewhere. So the electrons in the lab collider, in fact, they were a brightly glowing ring because of the synchrotron radiation. The protons in the LHC, although the energy is 70 times higher, is barely visible because it's practically zero. Okay, guys, I know this was a hard calculation. I also know I could not see your faces. I hope anybody, let me check if somebody is still connected. Yeah. Oh, okay, lost nobody. I know this calculation is hard. I would usually do it on the blackboard and go with you through every step more carefully, maybe as I did. As I said, there's a YouTube video. It's worthwhile to do it. It just gives you a feeling on how crazy the numbers are we are dealing with. You don't have a good feeling for particle accelerators if you haven't computed synchrotron radiation. It's also, and I promise, it's the most complicated calculation that we are doing. So in the first lecture, we are already above the peak. Now we can have some more fun, I suppose. Maybe it's time for a break. Lucas wrote me something on Skype. No, he didn't.
Kann ich kurz was fragen zu dem?
Ja, we can, for the questions we can ask, we can switch to German. Bitte, ja, frag.
Ja.
Ich bin froh, dass ich mal was höre. Ja.
Ja, also ich wollte fragen, also das, was quasi bei der Herleitung rausgekommen ist, ist quasi, dass es von der Masse von den beschleunigten Teilchen abhängt.
Richtig.
Und gibt es irgendwelche Projekte oder so, wo man andere Teilchen verwendet als Protonen, also noch schwerere, oder könnte man dann das nicht mehr quasi die Produkte auflösen?
Wir am LHC beschleunigen wir auch. Maybe I should answer in English because I put it on YouTube. The answer is the following. So the question was whether we have heavier particles, and yes, we do. And the heavier they are, the less synchrotron radiation is important. We collide, for example, lead ions. Lead ions have a charge number of 82 and a mass number, I forgot, but much higher than 100. So yes, it's more easy to accelerate and to collide heavier particles. Unfortunately, those are not fundamental. So we learn less because a lead ion, and Blair ion, is just a can of garbage. I mean, it's an enormous amount of quarks and gluons sitting on top of each other. We can study hydrodynamic properties of quark-gluon plasma. Yes, we can accelerate them. It's absolutely no problem. But we are not going to learn much probably about the fundamental interactions. Does this answer your question?
Yeah, thanks.
Okay. So in fact, practically speaking, when I was very young, LHC started up. I followed every step because we were anxious. It took a while to commission the collider with protons. So we would inject just a handful of protons and shoot them from one quarter over the ring and then lose them, and then all around the ring, and then add 2 bunches and so on. And all this took months. Once proton running was commissioned, it took 1 day to inject the ions, because it's the same. It's absolutely the same. There's nothing to it. You can just inject the ions and use classical expressions to scale the needed currents for the deflecting magnets and for the dipole magnets. So this is it's absolutely easy. In fact, yeah. So it takes a very short time to switch the whole acceleration chain from protons to ions. Mild changes to the beam optics. That's it. Are there more questions?
Yes, I have a question.
Go on, Fabian.
If we were to increase the energy by orders of 4, for example, then plugging that into the formula would give similar results, because this would cancel the how much heavier protons are. So in theory, if we were to increase our energy by several orders, at some point, this dissipation energy would be relevant again.
Absolutely. Absolutely. Absolutely, you're right. It's just very far away for all practical purposes, but yes, it is so. Just run the numbers. I mean, what we can realistically do, let's discuss this when we get to the end of the lecture. I'm not sure if your hunch is towards this direction, but we're going to discuss the strategy update of particle physics. People are contemplating a 100 TeV collider for electrons and for, a 100 TeV collider for protons. That would be the next generation collider, which let's discuss this when we also understand what the limitation is from the magnets, okay? Because this we have not discussed. This was now synchrotron radiation. Let me tell you a little bit more. Are there more questions on synchrotron radiation specifically? I think your question will become more clearer at the end of the lecture. If not, let me take you a little bit. It's much lighter now, okay? Light information, lean back. About synchrotron radiation. Here I have a list of synchrotron radiation at accelerators. It's interesting to know well, as we've just discussed, that the synchrotron radiation is collimated and leaves the beam tangentially. That means you can very accurately calculate its spectrum and all its properties. That's great because you can do a lot of physics with it, in particular high precision measurement. So here synchrotron radiation at accelerators, these are different accelerators. Well, here's it's an old table, but here's the lab collider, Petra in Hamburg, which is the positron energy, the positron electron source for Hera, and you see the energy loss per turn. So we have it's the same number, should be the same, 700. Yes, it's 708 keV for lab. That was on the previous slide, and the other accelerators with less energy, which have much less loss per turn. Now, practically, it's not very practical to have a collider and then put an experiment inside the beam pipe just for synchrotron radiation or very close to the beam pipe. What people really do is one guides the electron beam, for example, upon ejection through an undulator. An undulator is an alternating arrangement of these magnetic poles. It makes a wiggle on the electron path, and from this acceleration, you can as well, you can calculate the synchrotron radiation similarly as we've done before. Maybe the calculation is more difficult, or you do it with a computer, it doesn't matter. But it means that here you can have synchrotron radiation again in a very controlled fashion, and then shoot the beam back or eject it. So practically undulators are often used for synchrotron sources. The picture here to the right is a synchrotron from the General Electric company, who first observed synchrotron radiation in 1946. And there's a fun story to it, because there were two scientists and they were sort of expecting to see synchrotron radiation at some point. So there's an electron, there's a small cyclotron in here. So they were looking out for it, and they had talked. There was a technician, and they had asked the technician to look into the chamber if he could see something. And the technician didn't know what to look for, but he saw something. And so synchrotron radiation was discovered, and later the technician claimed to be the discoverer, claimed the discovery of synchrotron radiation, because his eyes were the first ones to see what you saw. That's right. But the physicists were the first ones to tell the technician to look at the synchrotron radiation. So they clashed about the precedence in seeing synchrotron radiation. It was a bit of a fight, but okay. They checked the logbook, and they found out that it wasn't really, it wasn't only the technician, there was also a Russian spy whom they found out just because they investigated the quarrel over who had seen first the synchrotron radiation, because it was 1946, beginning of the Cold War. It was cutting edge science, and the Russians had injected a spy in the General Electric, in the synchrotron of the General Electric company. Fun story. Good. Today, synchrotron radiation is used in science, as we've just discussed. I put here one example of a big synchrotron facility. It's the Alba synchrotron. It's in Spain, near Barcelona. It has a 3 GeV storage ring. You can look at here. All these particle accelerators, they're circular. So these facilities all look similar, circular facility. I visited this place in 2016. I think it's impressive. You have this storage ring running through the experimental hall, and then there are extraction facilities where undulators produce synchrotron radiation, and the synchrotron radiation is then used for X-ray microscopy, diffraction, crystallography, and other studies of that require a highly controlled radiation field. In fact, if you have a good idea what to measure, you can book your time there. So this will go through a board and they will decide whether the physics question that you're having is worthwhile or not, and they will give you time to conduct your experiment. So nowadays, synchrotron radiation is something that you can, if you get the time, if you have good enough idea, that you can book in facilities. This is by far not the only facility. There are dozens. In fact, I put the link to the list on Wikipedia. Good. So we have synchrotron radiation. We know how it's difficult to accelerate electrons. Now we move to the LHC where it's protons, and we look at what the limitations are there. So the proton beam in the LHC is bunched. It is not continuous. Protons come in bunches, and there are 2,808 bunches separated by very roughly 70 centimeters. As I said before, I'm going to explain it now, but as I said before, radio frequency cavities are operated to accelerate the bunches. So the wavelength of the relative length scale, let's say it like this, is 70 centimeters. How does it work? One has a cavity structure like this. So there's a symmetry. Here runs the beam. Okay, I hope you can see the mouse cursor. The beam runs horizontally. It's a symmetry axis of this cavity. So you have the cavity structure that is driven with high power, high frequency electric field. The frequency is 400 megahertz. The frequency is aligned such that if you have a bunch like this, if the bunch enters in the first cavity, it feels a force. The next cavity, the force is in the opposite direction, but there is no bunch. It's then oscillating in time, that while the electric field is oscillating in time, that while the proton bunch moves from left to right, it always feels an acceleration. The protons never feel the backward force from the cavity that has the negative phase. So you see that. You see that every second cavity is filled and the proton bunches move with the speed of light from left to right. The microstructure of this electric field is, I mean, you have an electric wave going behind these proton bunches. Microscopically, you have a bunch of protons. And there are a few protons that are a little bit slower, and there are a few protons that are a little bit faster. And now, let's say the electric field, it is sinusoidal, and it is slightly behind the bunch. So that means the protons in the middle of the bunch are accelerated. The protons to the left that are a little bit slower, they are accelerated a little bit more, so they move a little bit faster. And the protons at the front of the bunch, which are a little bit too fast, they are accelerated a little bit less. And so this setting stabilizes the bunch structure, because the ones that are lagging behind get a little bit of a stronger kick, okay? And the ones that are more far across the beam, they see a little bit less acceleration. So by carefully tuning the frequency to the beam and to the bunch structure, one can stabilize it and hold together the bunches, because they would otherwise run away. Now let me tell you something that I found that I find absolutely crazy, because we mentioned it before. Very high power with very high frequency is very difficult to handle. We're talking about 400 megahertz. And we need megawatts. This is there's very few places in industry where you have such specs. It's only gigantic signaling stations need radio stations need this power, and they don't come close. So how is it done? The amplifier that's used to drive such a high frequency with such high power is called a klystron. It's something I should explain because it's simply fun how ingenious people are. So what is here? What's happening here? This is a second electron beam that's complete, that has nothing to do with the collider. There is a high intensity electron beam coming from a cathode, okay? So you heat, in principle, you heat matter, it ejects electrons, and it moves it moves at low energy. Then you have a microwave input into a cavity, into a puncture cavity. And by the same principle that we made, I just explained to you how the punch is stabilized, right? So if we have a continuous stream of electrons, and we guide it through a puncture cavity with a microwave input that's high frequency, low power. The kinetic energy of all these electrons is enormous. And now because of this puncture cavity, some of the electrons move slower and others move faster. So you let the beam move until a density wave builds up, okay? So you use this high frequency and to imprint a density wave at on a high kinetic energy electron beam, and at the point where this oscillation has its maximum, you make another cavity, and this one then has enormous power output because the density wave is enormous. It builds up, and a lot of kinetic energy of the electrons can be transferred to the microwave output here. That's how a klystron works. And then you collect the beam again, okay? In practice, it looks like this. So here runs the beam, okay? It's the proton beam coming through. Here are the radio frequency cavities, and it's coupled through a waveguide to a klystron that is not visible. It is behind there. So behind there is this klystron amplifier, and you can see that many of the acceleration principles rely on the presence of a second beam. And that's in most of the future design studies. Most of the future design studies, to achieve very high gradients, very high energy gradients, you need very high power with very high frequency. This is only achievable by a particle beam. So to sum it up, the klystron uses a continuous electron beam to imprint a microwave frequency, so very high frequency density wave that you then pick up with a catcher cavity, and this you use to accelerate. This you use to accelerate the primary proton punch in this case in the LHC, but it works the same way in almost all the colliders. In fact, I'm not aware of any other acceleration principle. Good. I think that's great. Of course, it's not everything. You need feedback loops for beam control. You need beam optics, one needs collimators, one needs beam screens, and other sensors to carefully monitor the presence, to carefully monitor the behavior of the beam across the ring. Before we go, we will say a few more words on this. Let's move to the main limitation. That's the last calculation for today, and it's trivial. It's by the standards we've achieved today, it is trivial. The limiting factor for LHC proton-proton collision is the dipole, is the field strength of the dipoles. Because we collide protons, and when we want to collide protons, they go into opposite direction. We need two different signs for the field strength. So we need two different dipole magnets. With proton antiproton, we could in principle use the same magnet, but we're using proton-proton for other reasons. So we need magnets with opposite polarity for the two different beams. So here you have the proton beam going in this direction, you have the proton beam going in that direction, and to bend it over this tiny radius of 27, this tiny circumference of 27 kilometers, we need the highest achievable magnetic field. The LHC has 1,232 magnets operated at 8.3 Tesla. These are superconducting superconducting magnets operated at 1.9 Kelvin, which means we need a lot of helium. Is superfluid. One magnet is 50 meters long, and the cooling pipes are filled with superfluid helium. So let's compute the limiting factor for a circular proton machine. The Lorentz for should I write it down? I don't know. Yes, maybe. The Lorentz force, you have it there. Anyway, write it down. The Lorentz force F is Q times Vxp. That's the Lorentz force given the speed, given speed is the speed of light, given the magnetic field B, then we want to know, and this we can equate with the change of momentum. That's the inward change of momentum, because we have a circular motion. So this is just frequency times p. Frequency times p means that wait, can I move this? No. Frequency times p means I'm sorry, I have to continue here. Frequency is v divided by the radius. I write the radius. No, oh God. Wait, let me try. Yeah. I write the radius as rho times p, and now we can equate it and compute. We can cancel the velocity, and we can compute that the magnetic field B equals P, the momentum. So for the LHC is 7,500, 7 TeV or 8 TeV, divided by the charge and the radius. The radius is not really the radius of the LHC, it is the Lama radius, which is related to the smallest Krümmungsradius, so the smallest curvature, because the ring is not completely circular. It's almost circular, but it's not completely circular, because we need straight sections for the experiments. We need other straight sections for the radio frequency cavities. This cannot be on a curved path, so they must be straight. So we lose a little bit of our effective radius, and it's only 2,800. I think if you divide the 27 kilometers by 2 pi, you end up with a little bit of a larger radius. So the effective bending radius is 2,800 meter, and we can rearrange this formula in the more important form. Let me try, is this one. The achievable momentum, or the energy, because it's ultra relativistic, it's the same, is charge times radius times B field, and that's limiting. So you want a large radius and you want a large B field. If you insert the numbers, for an proton momentum of 7 TeV, that would give you 14 TeV collision energy. That's the design of the LHC. Currently we have 6.5, but it's going to be increased now. And you put in the electric charge. It follows that B is 8.3 Tesla. And that's what we've designed the magnets for. As I said, we run with 6.5, so we currently run with a slightly smaller energy and magnetic field. So really large radius, give me a large radius, give me a large B field. In other words, give me a magnet that can tolerate that large B field. It's not difficult. It's not difficult to achieve 100 Tesla. It's possible. People do it. They shoot the current into a magnet that explodes. You get 100 Tesla. It's not what we are doing here. We want to operate the accelerator continuously, so it cannot explode. It cannot quench. It need to have structural integrity, we barely achieved the 8.3 Tesla. So that's really technologically challenging. So anybody who has a good idea how to build magnets that can tolerate more and can be operated at this scale would be responsible for the next generation proton-proton collider. To come back to Rosemary's question now, let's look at the collision of lead ions. The same thing holds. The momentum of the lead ion is the magnetic field that you have, it's the same, times the number of charges, because the charge of the ion is just C times the elementary charge, times rho. And this momentum is now spread up into the momenta of the nuclei that make up the ion, and that's the mass number. So we get an achievable momentum with a factor of the charge, because that's what helps us. And then this momentum is distributed among the whole nucleus, including the neutrons. Okay, because the difference between the charge and the mass number is the number of neutrons, including the neutrons. So if you compute the nucleon momentum for lead at the same LHC limiting factors, you have the 70 eV multiplied with 82, but divided by a mass of 2.08, which is per nucleus. In heavy ion collision, you only have 1.4 roughly tera electron volts, okay? But that's per nucleon. The whole ion beast has 208 nucleons, 82 protons, and the rest is neutrons. So the whole ion has 574 TeV. It's just a big object. That's why it has so much energy, okay? So that's a quantitative example of what happens in ion collisions. We're not going to talk a lot about ion collisions, but it is worthwhile to think about what's happening. I'm not sharing my face, right? I'm not sure I am. Ah, maybe I am.
Yes, you do.
I do, okay. As you can see, I sit in the LHC tunnel. No, realistically, I'm in lockdown as well. It's the attic of my parents' house, which is the only attainable quiet spot. But you see now a picture of the LHC that I also have in my background. This is one of the 15-meter longer magnets. There are 1,200 of them, which fill the largest fraction of the tunnel. The rest is straight sections for radio frequency cavities and for the experiments. Okay, that's the limiting factors of the LHC. Let's look a little bit on what these things look like. The magnets. So here's the cryodipole in a different drawing. Inside here you have the two beam pipes running. This whole thing is roughly 1 meter the diameter is roughly 1 meter. So here run the beam pipes. That's what a beam pipe looks like. It's it's a complicated design. It needs to shield the mirror currents, which you otherwise have because we're passing through fairly high currents, and it needs to be cooled. And so here in these pipes runs the superfluid the superfluid helium. The critical part is where the magnets are soldered. This is where the really critical part is. You have a superconductor. These are all superconducting magnets. Superconducting magnets are built from superconducting cables. Superconducting cables, you can test them above ground and you can commission them. And if something is wrong, you throw it away. And then you make your magnet, and that's still fine. You test your magnet above ground, and if it doesn't work, you repair it. But once you are underground, you have to solder the magnet. And if you have a problem there, it takes a year or 1.5 years, because you need to remove the magnet and install a new one. Warming up takes a month, cooling down takes 3 months, and then you have your repair, so you are more than a year. It has happened once in 2009. We had a quench, a catastrophic quench at one of the junctions of 2 magnets. The soldering had to be developed. You cannot really solder superconducting cables. It's very difficult because the soldering material will not be superconducting. We have nano-ohm resistance between these junctions. And nano-ohms times 20 kiloampere is what is carried away by the cooling of the superfluid helium. It's a system that works. However, if there's some problem at the junction, the current, the ohmic resistance explodes from nano-ohm to milliohm. That means you get enormous heat deposits, and the superfluid helium evaporates very quickly. That's how the cooling functions. And this evaporating helium needs to pass through valves. You need to remove it again because you cannot build up the pressure. And that's what failed in 2008. I think it was 2008. And so there was one problem at the LHC startup where we had a quench at one of these junctions, and the evaporating helium could not be released through the valve, which had too small, it was under dimension. So there was a spark and essentially an explosion. 20 kiloamps melted a radius of 2 meters. Everything was melted. 24 magnets, they are 15 meters long, okay? 15 meters long. So we're on a stretch of more than 100 meters. The magnets were kicked out of the concrete they were resting in. So this was a major accident, and it cost us a year to repair. So we've learned a lot about soldering superconducting cables, I can tell you that. We also know now which companies can do it and which companies we don't trust. But since 10 years, since 10 years the machine is commissioned, and aside from this failure in the beginning, it operates flawlessly, more or less. It operates beautifully. We have higher than design availability. Good, so much to the magnets. Let's look at the beam. The LHC beam stores 4 terawatts of power. And the beam has 360 megajoule. The bunch, a proton bunch has roughly 100 billion, so roughly 200 billion, 2 times 10 to the 11 protons. If it hits material, this is what it looks like. And that's 1 of 2,808. So it really, that's destruction, because our sensors are micrometer thin. The beam is punched, as we said, it's 2,808, and they run counterclockwise. That's not, I mean, this is not 2,808, but you get the idea. There is an opening gap. Yeah, there's an opening gap in both beams that run in the 2 different directions, which lasts for 3 microseconds. That means we need to decide across a facility that has a circumference of 30 kilometers. We need to decide within 1 microsecond whether the beam needs to be damped, okay? It could be that the sensor senses a failing vacuum. You need to know within microsecond across, I mean, this is a large distance. You need to know that the beam has to be damped. If it is damped, there's a kicker magnet. The kicker magnet is ramped. You see here the kicker rise time, it is ramped, while the window is opening, while the window is open. When the kicker magnet has risen within this window, the beam is deflected and shot in a beam dump facility where it causes destruction. It melts, so it cuts into an aluminum block 1.5 meter wide. So it cuts into therefore 1.5 meter while it is moving at a very high speed. So you have it's like an absolutely intense material laser that cuts the aluminum in half at the depth of 1.5 meter while it is moving. So this is all under control. The worst thing that could happen, just to give you an idea about the danger, that the kicker magnet starts kicking while the window is not open, because then it kicks the bunches out of their orbit, and they would wiggle around in the magnetic field, and they and the protons would violently hit the detectors. This would cause destruction. So the big safety aspect, I mean, not for people, there's nobody down there, but for the detectors, so for the money that we put into and for the physics. So the carefully designed thing in the whole LHC, or among the most carefully designed, is the logic that lets the kicker magnet start. This is really absolutely important. So here's the beam down. This is what the kicker magnet looks like. Essentially, it has just one winding, and you have a huge capacitor that you shoot into there, because you need a below microsecond rise time, which isn't easily achieved otherwise. Okay, the bunch spacing of the bunches in the LHC is 25 nanoseconds. So every 25 nanoseconds, a bunch comes along. We'll discuss about the consequences of that. Let's look at the beam a little bit more. 360 megajoule. Design stored energy is 700 megajoule or something. If you could stop the beam, it would deposit 10 terawatts, and the 2015 world energy production was 13 terawatt. So while the beam is deposited, which happens in very roughly 10 to the -4, so 10 microns, I'm sorry, 100 microseconds. It deposits 13 terawatts. The comparison I always show is the gunship here firing with its 16-inch cannons. That has a 300 megajoule. So what you have in the detector is two of these gunships firing at each other, and all the kinetic energy goes into the proton bunches, and they collide at the center of the detector. Bunch spacing is 25 nanoseconds. 25 nanoseconds means a collision rate of 40 megahertz, and there are roughly 115 billion protons per bunch, and this leads, we will run the numbers, but this leads to 25 interactions per bunch crossing. So with a rate of 40 megahertz, we get 25 or so collisions. Good. We've talked about a lot concerning beams, energies, energy frontier. Now we need to talk about luminosity. Luminosity is a concept that it's actually very simple. You're probably just not used to it. When you do a little bit, when you do some small work as a student, it's the first thing that you learn. Let's look at the fixed target experiment now, okay? This is not colliding beams, this is fixed target. I have a volume here of a constant density. The density is rho. I write down the unit of the density is let me write it here, is meter. Is meter to the -3. So particle per cubic meter, if you want. Okay. We shoot a beam of particles with a rate of phi. That's the number of beam particles per unit time. And we have our detection length here is L. So this means the rate of the interaction. What's the rate of the interaction? The rate of the interaction is the rate of incident particles per unit time. So we have seconds. We have per second times the density times the length of the detector. That's in units. That's meters. And then we need a probability. We need something that gives us the reaction probability, but that's under quotes. It gives us an idea about how likely it is that a cross-section, that an interaction is happening. And this quantity is the cross-section. The cross-section, you can view it, I mean, it has the dimension of an area. So it is meter squared, okay? You can think of a proton, or you can think of a fixed target like it is depicted here, and you shoot at it with small particles. You can then derive from the size of the object the geometric cross-section, which will be just the area of the object that your small probe sees. That's why this reaction cross-section always have the units of area. Because it has the unit of area, the luminosity has the unit of inverse area. Okay, so the rate of events is given by definition from the cross-section, and everything that comes as a prefactor. And from our simple expression, we can read off the fixed target luminosity expression. The fixed target luminosity expression is the rate of events times the density of the target times the length. So you see that the luminosity is in fact a product in principle of two numbers. The one is the number of events that we shoot in, it's n beam divided by delta t, and the other number is given by the density, so it's rho. It's the density of the particles in the target. Each of these quantities increases the number of reactions that happen per time. We are not going to look into fixed target experiments a lot, but the expression for the luminosity is phi, the rate of events, times rho, the density, times the length here. Can erase this again. What I do want you to memorize, and what's really important, the unit of the cross section conventionally is centimeter squared, and the unit of the luminosity is centimeter to the -2 per second. That gives you the rate of events per second, and when you integrate it over time, you get what we call the integrated luminosity. We define this by L, and this one has units per centimeter squared. So these are the things that you have to know by heart. The luminosity is inverse centimeter squared per second, and the integrated luminosity is inverse centimeter squared. Okay. Why this separation of these factors? The cross section. Let me say this again. The cross section. This is physics. This is what you want to know. You want to know how often do you produce a Z boson or a dark matter particle or a Higgs boson. That's in the cross section. This L here, the luminosity, that's detector. Detector facility. Detector maybe only very indirectly. Let's erase it. The luminosity is facility. It's given by how much you can focus your beam, how many protons you can fit into your bunch, how many bunches you can fit into your beam, and if you integrate it over time, what's the availability over the whole year to operate your collider? Okay, so we have facility times physics. Oh, and it looks like the two are married here to produce event rates. Okay, that's what I want to say about luminosity and cross-section. This is important, okay? So here's the first thing that you really have to understand: luminosity and cross-section and event rate. I'm going to discuss it 100 times. That was the first time. Now we look at, again, at the fixed target experiment, okay? We do relativistic kinematics. In case you don't understand relativistic kinematics, you need to send me an email and I will give an introduction. I'm assuming you understand relativistic kinematics, and I've used it a lot in the derivations today. So in case this was too much, you have to tell me. Let's use it. We have the form momentum of the beam particle. It's ultra relativistic, so we can forget about the mass. So here's the energy of the particle. And we have the form momentum of the target. It's at rest. So here we have just the mass. That's it. Let's compute the center of mass energy, because that's the energy that's available to produce new particles. And after all, that's what we want to do. So if we do that, we have the beam for moment, the beam particle for momentum, and the target for momentum. And this is E plus m squared minus E squared. And this I achieve by inserting these guys here and evaluating the form momentum. It's just E plus m squared minus E plus 0 squared. And the result is 2em plus m squared. And we take the square root. We can forget about this term. So if the mass is much smaller than E, this just becomes square root S is just square root of 2em. That's actually very, very bad for fixed target experiments. Why is it so? Because if you compare this with a beam-beam collision, the story is completely different. There you have, instead of the target, you would have E 0, 0 minus E. And if you run the computation again, you get square root S is 2E. So in one case, let's do some, let me erase this and compare this. Let's say we have the LHC beam, okay? And two counterclockwise beams, and they collide in the detector, and it's 6.5 tera electron volt. So square root S in the beam would be 2 times 6.5 tera electron volts, which is 13 TeV, which is indeed what we achieve. Let's say we don't do beam-beam collisions, we shoot it at hydrogen. So hydrogen is just protons. Let's make a fixed target experiment. We take the LHC beam, but we shoot it at hydrogen. What's the center of mass energy? It's the square root of 2 times 6.5 times of 6,500, we write in GeV units, times 1, because that's the mass of the proton. And this will be a much smaller number. That's, who can do it? Okay, I did not, this is one thing I did not prepare. Let me very quickly calculate it, because I want to know. So that's 2 times 6,500. It's 114. Now I need to find back my, okay. So this is 114 GeV. In other words, it's hopeless to do high energy fixed target experiments. You need beam-beam collisions. Although it's much more difficult, unfortunately, but that's what it is. So I advise you, please, to check this calculation and to run the numbers, because if somebody asks you, like say from the Ministry of Science in Austria, they would ask you, why do you need so much money for these facilities? And you got to tell them, well, we need beam-beam collisions, and we need 2 beams. And we need that because we need to go to the highest energies possible. And no, we cannot do fixed target experiments like the low energy physics guys do, because it's just too inefficient. And the answer is in these 2 equations here. All right. Let's look at the beam luminosity. I told you I'm going to do the beam luminosity calculation next time. I have prepared it, but it's only 15 minutes left. And I do not want to stress you out with another calculation. This one is much simpler. You can do it by hand. You just follow the math here. These are just Gaussian distributions inserted in the beam luminosity. I will nevertheless do it next time because I think we've worked enough for today. Let me just tell you in words. We'll do the calculation next time, and it will only take 5 minutes, not 50 minutes, just 5. We can calculate easily the luminosity that is provided by 2 bunches that collide. And because we have 2,808 bunches colliding with a frequency of, with the revolution frequency of the LHC, which is 11 kilohertz, we can compute very easily the LHC design luminosity of 10 inverse nanobarn per second. I want to end today's lecture by going again at luminosity and cross-section, because it's really very important. It's at the heart of what we are doing in at the different facilities, and with the calculation I just skipped, we can do it next time. But I want to talk now about magnitudes and scales. So the unit of the cross-section is a bar, okay? I've said this in the beginning of the lecture. A bar is 100 square Fermi. A square Fermi, I'm not sure if I want to draw this again, but a square Fermi, 100 square Fermi is a rectangular grid of 10 Fermis in 2 dimensions, and with 1 Fermi of the size of the proton very roughly at the center. So 100 square Fermi, 1 barn, is a very large cross-section. It's 100 times the size of a proton. In units, it's 10 to the minus 24 centimeters squared. Conventionally, I don't know why, we always use centimeters squared. I don't know why it is. It's SI units, nevertheless. The instantaneous luminosity of contemporary colliders at the luminosity frontier is 10 to the 34, that's for the LHC, and up to 10 to the 35, that's for a plus and minus at super KGP in Japan, okay? So what you now have to do is to multiply the luminosity with the cross-section of the process of interest, and you will get your event rate. And I want you to spend today's lecture, I mean, the second part of today's lecture is summarized in principle here. So we have the collider with the synchrotron radiation that limits the plus and minus colliders. We have the magnets that limit the circular proton machines. And now we have luminosity that tells us what are we going to see. 10 to the 34, 10 to the 35 centimeter inverse squared per second for the best machines that we are having currently, LHC, Super KKP. Let's look at proton machines. Proton machine has 80 millibarn. 80 millibarn is 0.08 barn. It is, in principle, 8 proton. It's 8 times the area of a proton in my simple picture from before. This is the cross-section of a proton-proton collision. This should tell you that if you compare this with the geometric cross-section of a proton, which is just one, which is less than 1 Fermi squared, this is an enormous cross-section. The cross-section of the reaction is much higher than the geometric cross-section of the proton. The reason is that the proton is strongly interacting. It's full with gluons, and these guys come close to each other, immediately something happens. So if you multiply this 80 millibarn proton-proton cross-section with the 10 to the 34, 10 to the 34 or so, we have 10 to the 34 LHC design luminosity, you find enormous rates. This is the, here's a list of cross sections for LHC processes. So here is where we currently are at an energy of, square root of S that was for 8 TeV, it was in run 1, we were here. It doesn't matter really very much if we are here at 8 or if we are here at 13. These cross sections do not depend a lot on the energy. But we have 10 to the 34 times 10 to the minus 24. That means 10 to the 10 per second, okay? So we have billions of collisions per second. Gigantic numbers, nobody can record this. Each collision would give you roughly a megabyte of data, 1 to 4 megabytes of data in the detector. It's absolutely impossible to store this. But this is just what happens in a proton-proton collision. We know what happens in an average proton-proton collisions. We can calculate it. We're going to do that in the next, we're going to look at this in the next lectures, but these are not the interesting processes. So what we're really interested in is these processes very far down here. So here you see this is a logarithmic axis. The cross section here is 80, it's roughly 100 or 80 millibarn. That's everything that ever happens if two protons collide. But if you also want to see a W boson, or you want to see a Z boson, or you want to see in red here, you want to see a top quark pair, then you are many orders of magnitude lower, okay? So here we have, if you take the numbers at 10 to the minus 1 roughly nanobarn times 10 to the 34, gives you very roughly 1 TT par pair, 1 pair of top quarks per second. And that's very easy to record. It's just 1 megabyte per second for the top quarks. If you look at the Z bosons at the LHC, you run the same numbers, it's 2 orders of magnitude higher, so we get very roughly 100 Z bosons per second. It's also doable. We can record with the CMS detector, we can record roughly 800 events per second. So we can record all Z bosons, and we do. So these are typical LHC rates. I want you to look really closely at this formula. The event rate is the luminosity in centimeter to the minus 2 per second times the cross section. So event rate really comes out with s to the minus 1. And the number of events of your process during a long period of running, this time integral extends over many, many years of operation, is of course the time-dependent luminosity, because sometimes the beam is better, sometimes it's worse, times the cross-section, times the efficiency. Luminosity can be given in inverse barn per second, and the cross-section is given in barn. Integrated over time, this gives you a number of events. So you can now take your favorite collider project, look at the cross-section, multiply the two numbers, and see how many events you would get. And that will tell you whether you can actually look for the Higgs boson, for a supersymmetric particle, for a dark matter particle, and so on. We're almost done for today. This was the LHC. It's a proton-proton collider. See, it has a gigantic cross-section of 80 millibarn. At the lab collider, that's an E plus E minus collider, the cross-section is much lower, okay? We talk about 10 to the minus 5. Look at here, this is where the lab was operated, at the Z-pole mass, okay? The cross-section here is 10 to the minus 5 millibarn. So instead of 80, you have 10 to the minus 5. This is because the electron is not strongly interacting. It's also not composite. It's elementary, and it interacts electromagnetically and weakly, and that's it. That leads to a reduction in the typical cross sections by very, very large factors. Here it's 5 orders of magnitudes. This means that at the lepton collider, you can record all events. It's possible. Even at the luminosities that we're having now, a trigger is not, I mean, there are triggers, but it's not as important, by far not as important as at the proton-proton colliders. The trigger is the logic that decides whether we record an event or whether we drop it. At an E plus E minus collider, it's not so important, because if you see something, you can record it. The cross-section are so low that even at the highest luminosities, the rates are tolerable. While at the proton-proton machine, the 80 millibarn has such a large cross-section that at realistic luminosities of 10 to the 34, you get billions of events per second. I put here a beautiful measurement from lab. This is the cross-section of E plus E minus collisions as a function of the collision energy. We have here the Z peak, that is the Z boson. We have here epsilons, psi2s, J psi's. These are C-quark bound states. And here we have the lower energetic, the lower mass mesons. We will look at this in some course detail. But I will tell you mostly about experiment and not about the theory that predicts these particles. But nevertheless, look here at the Z boson. And in the plot below, you see the production cross-section in picobarn, so that's a tiny unit, versus the center of mass energies of an electron and a positron colliding. And you see that at a threshold of 180 GeV, you begin to produce, we have interesting processes with two Z bosons. A Z boson has 90 GeV. So 2 times 90, around 90 GeV. So 2 times 90 is 180. So once you have more center of mass energy than the masses of these guys, they start to appear in your detector, although at an extremely low rate of just 1 picobarn. You don't have to learn the details here. It's not important exactly where these how high these cross sections are, but it's interesting to see. I mean, that the W has 80 GeV, so the WW begins at 160 GeV. Photon is massless, so for all energies you produce photons. A Z boson has 90 GeV. The plot only starts at 100. It begins where this other plot ends. So if you go further down the energy, you leave the plot here and you enter this plot here, and you see all these interesting processes popping up that you can then measure and compare theory with experiment. Good. I skipped today this other light stuff that we can discuss next time. But I wanted to convey to you cross-section and luminosity. That's it for today. It was a lot. Are there questions? So, are people still there? That's my first question. Yes. Do you have any questions? Maybe we can also make a question session next time if you want. You can just speak up. Okay, doesn't matter. Wait, where is this? I thank you very much for your attention. I say again, I know we went through a lot of material. Next time, I'll tell you about I'll do the luminosity calculation, which takes a few minutes for the bunch crossing luminosity, and then we move on to studying a little bit collisions. But for today, I think we are done, and I will also maybe post, until next time, I'll post a list of questions that I'm going to ask, and you'll see that I've explained to you much more than I'm going to ask at the exam. Okay. Any more questions? If not, I think we can close. I will stay connected if somebody changes their mind, but the lecture is over, and I wish you a nice afternoon and see you next time. Goodbye.
Bye.
Thank you. Bye.
Thank you. Bye.
So, stop sharing.